The Tuple Serialization Registry maintains a hierarchical mapping of type identifiers to their corresponding marshalling routines. Each entry in the registry contains metadata defining how a particular data structure should be encoded and decoded during persistence operations. The registry is initialized at startup and persists for the duration of the process lifecycle. Type identifiers follow a 12-bit unsigned integer format, allowing up to 4,096 distinct types per registry namespace. The identifier space is partitioned into reserved ranges for built-in types, vendor-defined types, and user-registered types. All identifiers are assigned sequentially upon registration and cannot be reused within a single process lifetime. Each marshalling routine implements a standardized interface consisting of encode and decode operations. The encode operation accepts a tuple instance and produces a byte sequence suitable for storage or transmission. The decode operation reverses this process, reconstructing the tuple from its serialized form with all fields restored to their original state and type. Field resolution occurs through a dual lookup mechanism. The primary lookup uses field index positions established at type registration time. Secondary lookup by field name is available for all registered types but incurs additional overhead proportional to the number of fields. Both mechanisms must return consistent results for the same field reference. Type compatibility checking evaluates structural equality between a serialized type definition and the current runtime type. Fields must match in count, order, and type. Optional fields are tracked separately and do not block compatibility when absent from older serialized data. Incompatible changes trigger a versioning mechanism for graceful migration. Nested tuple structures are resolved recursively through the marshalling system. When encoding a tuple containing another tuple field, the system invokes the marshalling routine for the inner type. Nesting depth is limited to a configurable maximum, defaulting to 32 levels. Circular references are detected and rejected at registration time. The marshalling registry maintains an in-memory hash table indexed by type identifier, providing constant time lookup for encode and decode operations. A secondary index by type name offers name-based resolution with logarithmic lookup performance. Both indices are kept synchronized during all registry mutations. Null and sentinel value handling is defined per field during type registration. A field may be marked as nullable, allowing null values to pass through serialization without error. Sentinel values are encoded as special markers in the byte stream, occupying a single byte of overhead per sentinel field in the tuple. Endianness and numeric representation are standardized across all marshalling routines. All integer types are encoded in network byte order, with sign bits handled identically regardless of platform. Floating point values use IEEE 754 double precision encoding. No platform-specific binary representation is permitted in the serialized format. String field encoding uses UTF-8 encoding with a 4-byte length prefix. The length prefix specifies the byte count of the encoded string, not the character count. Null strings are distinguished from empty strings through a special marker value in the length prefix, consuming a total of 4 bytes. Collection fields such as lists and maps are encoded with a 4-byte element count prefix followed by serialized elements. Map keys are encoded before their corresponding values. Collections maintain insertion order in the serialized form, but are not guaranteed to preserve order upon deserialization unless the target type explicitly supports ordered semantics. Schema versioning allows types to evolve over time without breaking backward compatibility. When deserializing older data, fields that existed in the old schema, but not the current schema, are silently discarded. Fields present in the current schema but absent from the older data are initialized to their default values. Custom marshalling implementations may be registered to override default behavior for specific types. Custom routines must adhere to the same interface specification as built-in routines. The registration system does not validate custom implementations and assumes they produce byte sequences compatible with their corresponding decode routines. Error handling during marshalling follows a standardized propagation model. Encoding errors are surfaced immediately and prevent serialization from proceeding. Decoding errors are categorized by severity. Recoverable errors allow partial tuple reconstruction with defaults, while fatal errors halt deserialization and return an error condition to the caller. Performance characteristics of registry lookups are dominated by hash table access time, typically averaging 2 to 4 microseconds per encode or decode operation. Bulk operations on collections reduce per element overhead through batching. Registry operations are thread-safe through fine-grained locking on individual type entries. The marshalling registry lifecycle begins with initialization during process startup and ends at shutdown. Types registered during runtime persist until explicitly unregistered or until process termination. Unregistering types is not recommended for active types and will raise an error if tuples of that type are currently serialized in memory or in flight.